As the Gaia spacecraft has mapped more and more of the Milky Way, astronomers have uncovered some of the fastest-moving stars in the galaxy. Can simulations link these stars to the elusive origins of type Ia supernovae, occurring in binary star systems with at least one white dwarf? Type Ia supernovae are key cosmological distance indicators and have allowed astronomers to study the expansion of the universe. Despite their importance, the details behind these explosions and the characteristics of their progenitor systems remain unclear. One proposed mechanism to launch a Type Ia supernova is the double detonation scenario, in which the white dwarf accretes helium from a helium-rich donor star. Forming a thin shell around the carbon-oxygen core, the siphoned helium eventually detonates, sending shock waves through the core, causing it to also detonate. In the wake of the powerful explosion, the donor star launches across the Milky Way, forever changed. Recent Gaia discoveries of a runaway, helium-burning star and hypervelocity stars, stars that zoom through the galaxy much faster than the general stellar population, suggest that the double detonation scenario may be responsible for a number of Type Ia supernovae. Can double detonation simulations predict the observed properties of these fast-moving stars, further uncovering Type Ia supernova origins? As a helium-rich donor star is bombarded with material and energy from its exploding white dwarf companion, interactions with the supernova ejecta can leave lasting impacts on the donor star's trajectory through the galaxy, as well as the star's properties and evolution. Motivated by this interaction and the Gaia observations of hypervelocity stars, Tin Long Sunny Wong, University of California, Santa Barbara, and collaborators performed hydrodynamical simulations that track, with novel clarity, the lasting imprints supernova ejecta leave on their companions. The author's analysis shows that as the supernova ejecta crashes into the donor star, some of the donor star's material is swept up and pulled in the direction of the supernova's propagation. The supernova shock wave passes through the donor star, both compressing and pushing the star away from the explosion center. As the shock front moves on, the donor star attempts to return to equilibrium, contracting and expanding, sending smaller shock waves into its surroundings. For each progenitor stellar type simulated, the authors find that the donor stars become puffed up with lower densities and larger radii. The donors also lose some of their original mass, but acquire a small portion of supernova ejecta material, consistent with the observed metal-polluted atmospheres and larger radii of hypervelocity stars. Particularly important to the identification of donor stars in the field is how these stars evolve over longer timescales and how we may observe them today. The authors performed further simulations to track the temperature and luminosity changes for each simulated donor star from 10 years to 100 million years after the supernova event. Intriguingly, some of the observed hypervelocity stars seem to fall near the predicted evolutionary tracks, suggesting that these stars could have been ejected by Type Ia supernovae. This study provides important evidence for the possible double detonation scenario of Type Ia supernovae. As simulations continue to improve, the ability to identify the progenitor systems of these energetic events becomes more promising.